Thank you. Thank you for having me. All right, so this is, I want to say two things. First of all, this is probably the most fun math project I've ever been in. So I want to not only tell you about the math in it, but also explain why it's fun. And the other thing is it started here, because it was a week that Dan and Alessia were visiting the IAS, and Tara and I were here for the semester, and then we just started talking about it. It was like very happy math happening. Okay, so I'll first talk about the basic question for symplectic embeddings. Is very easy to pose. Given two symplectic manifolds, when does a symplectic embedding of one into the other exist? Right, and so there, to have the complete question. Okay, and it's a very sort of easy question to ask, but of course it's very hard to answer. So I'll give you I'll talk about three partial answers for very specific examples of M2, which will both show how complicated answering this is and also introduce the topic of infinite staircases. So maybe the most celebrated answer to this question is Gromov's non-squeezing, in which for M1 you have a ball of radius r, and you want, unless I say anything in contrary, all my manifolds are open and subsets of C to the n. So you want to embed this into a cylinder, so that would be D2R cross C, different R, little r. And when can you do this? Very complicated answer, or sorry, very complicated math, very simple answer. It's just if you can actually just include the ball into the cylinder, right? So you can't squeeze it. Right? Yes, it has. Oh, not yet. Okay. Then another partial answer is when M1 and M2 are both ellipsoids. So an ellipsoid is, and now I'm in 4 dimensions, so I guess n equals 2. Z1, Z2 in C2, though of course you can define bigger ellipsoid just with more parameters. Z1 squared over A, Z2 squared over B, smaller than or equal to, oh, I'm missing some pi's. I said open, okay? So then here the question is, when can you symplectically embed an ellipsoid into a slightly different ellipsoid? And the answer, of course, has to do with the numbers A, B, C, and D, but sort of in a very combinatorial way. And C, D for all K. And I should tell you what these guys are. So NAB and NCD, these are sequences. So sequence formed by, you take all integer combinations of A and B, and then you order them. Okay, so formed by all positive integer combinations of A, B in who is squared? Oh, the A and the B? No. No, I think this is in non. Yeah, I think it's so that the area is like A times B. Yeah.
Do you assume that A is less than B? A is less than B?
Well, very soon I'm going to assume that A is equal to 1 and that B is called A. But I don't think you need to assume that. I mean, you get the same sequences. So sequence formed by all positive integer combinations of A and B in non-decreasing order. So, for example, if I have n 1, 4, that will be positive. Maybe I should say non-integer combinations. I want to consider 0 as, so maybe I should say non-negative. There. So what I mean is just linear combinations where the coefficients are integers. So 0, and then I can get 1, and then I can get 2 by doing 2 times 1, then I can get 3. I can get 4 in 2 different ways. And then I can get 5 by taking 5 of these or 1 of each. 5, 5, 6, 6, 7, 7, 8, 8, 8, 9, 9, 9, and so on. So it's very regular. And for example, if I have n 2, 2, then again I can get 0 in one way. I can get 2 in 2 different ways. I can get 4 in 3 different ways. I can get 6 in 4 different ways. I can get 8 in 5 different ways, and so on and so forth. And so we can see that the top sequence is always smaller than the bottom sequence. And by this theorem, this means that E 1, 4 embeds symplectically into n22, which, by the way, is, sorry, not n. Which is just the ball of radius 2. So a couple of things. These are, I should give names to, these are the sequences of ECH capacities of the ellipsoids, and I'll talk very briefly about ECH capacities in about 15 minutes. Now, let's see. This direction is first due to Hutchins when he introduced ECH capacities, and this direction is due to McDuff. Okay, so then another question that I can ask is, I could say, well, could I do a little bit better? Can I put a slightly bigger ellipsoid into this ball? Well, in this particular case, the answer is no, because this has the same volume as that, which you can't, symplectic embeddings preserve volume. So, but I could ask, well, what if I did like something with slightly different ratio over here, like 1 point something and 3 point something very large? Could I then embed it? So the next question, number 3, is exactly about this, about what shape ellipsoid, or how big a ball you need to fit different size shaped ellipsoids. So if I'm just worried about the relative ratio of the A and B, I might as well just call it E1A. And then a ball of radius lambda. That's E lambda lambda. And I can summarize this whole question in embedding capacity function. C of A is equal to the infimum lambda such that E1A embeds symplectically into lambda, so the smallest ball in which you can symplectically embed the ellipsoid. A couple of quick observations are that for symmetry reasons, you might as well assume that A is bigger than or equal to 1, because the other direction, and the other A smaller than 1, you just think of the symmetric problem. So another quick observation is that C of A is always C of A is always smaller than or equal to A, right? Because I can always just include E1A into the ball of radius A, and a little bit more interestingly, always bigger than or equal to the square root of A. And that's because this has a volume on the order of lambda squared, and this has a volume on the order of A. And the constants, the pi's, work out. Okay, so let's see what this graph looks like. So this was studied by, I always think it's like with the optional C. I think it has a C. I think it has a C here, but not there. Okay. All right. So here's square root of A. It's A. And here it is. Okay. So at 1, E1A is just the ball of radius 1, so it starts right there. And then as we increase A, so my ball is just getting more oblong, then how big the ball has to be just increases linearly up to E12. So E12 just has to be included in the ball of radius 2. There's nothing better that you can do. So that's a lot like this Gromov non-squeezing business. Then you have this ball of radius 2, and you have this ellipsoid sitting in there. You can actually do much better. Now you can increase the size of the ellipsoid, and it still fits in the same ball. And it actually will fit in the same ball all the way to the ellipsoid E14. Okay? And then sort of the same thing happens. Your ellipsoid is now all sort of folded up inside your ball, and now if you make it a little bit more oblong, your ball has to increase linearly. This will actually be aligned through the origin until it gets to 5, E15, and then it goes straight again, and then again aligned through the origin, and then straight, and it keeps going like this, straight line through the origin, straight line through the origin, until right here at tau to the 4th. So smaller and smaller like staircase steps. So that's where the infinite staircase name comes from. So here from 1 to tau to the 4th, we have a staircase.
What's tau to the 4th?
Tau is 1 plus square root 5 over 2, the golden ratio, which is nice. It's nice when that shows up in a math problem about symplectic geometry. Well, about anything. Okay, now I'm going to skip what happens here. I'm going to talk about what happens at, I think it's 8 and 1 over 36. From here forward, so now your ellipsoid is really very much like a sausage. From here forward, there's it just fits. It's just a volume constraint. So you can just you just take a ball with the same volume, and it somehow you can bend it all inside. So here it's C of A equals to square root of A. So this is just the volume constraint. And from here to here, so over here I have no symplectic obstructions. Here I have clearly some obstructions that are not the volume, so they come from the symplectic geometry. From here to here I have sort of a mixed behavior. Most of the time it's equal to the volume, and then it has some intervals where it has little steps. Okay? But so maybe I'll write here mixed behavior. So this is really amazing that such an easy question to pose has such a complicated, intricate-looking answer. I think to add to the amazingness, maybe I'll say that, so this these, which one am I saying? The interior corners. So this is 1, 1. This is 4, 4, 2. This one is 25 over 4, 5 over 2. So these interior corners, 1, 2, this should be 1 over 1, 2 over 1, 5 over 2. The next one is 8 over 5. So these are ratios of, 13 over 5. These are ratios of Fibonacci numbers. So interior corners are g n plus 1 squared over gn squared, comma, gn plus 1 gn. So in the x and y coordinate, of course, because they're on the volume constraint, this one is square of that one. And I should say g sub n equals nth odd indexed Fibonacci number. Okay, so this, for that reason, this is called the Fibonacci staircase. So somehow, now you have Fibonacci numbers appearing, which again is very pleasant because math is amazing. It does also mean that it's not so surprising that the golden ratio shows up here. But still, you traded one mystery for another mystery, so it's still a good trade. All right. So the way that Dusa and Felix proved this is very complicated. It's a very long paper, and they compute this. They use like Cremona transforms and some continued fractions, and of course also moduli spaces of J-holomorphic curves, because what else are you going to use? It's very, very complicated. I guess I can write over there. Okay, so more generally, we can ask this question not just about the ball, but about any four-dimensional symplectic manifold. So you can just define C of A as the smallest lambda, such that E of 1A embeds symplectically into a lambda scaling of x. Okay? And indeed, people have asked this question. So let's see, they asked this question for x equals to the ball. So this was, you get the Fibonacci staircase. So this is due to, I said there, McDuff and Schlenk. 9. Then it has also been studied for when x is equal to the polydisk. So just d2 cross d2. And here you also get an infinite staircase. It's it involves, instead of the Fibonacci numbers, it involves the Pell numbers. It's another recursive sequence. So Pell staircase. So this would be Frankel 2012. It has also been studied for when x is just an ellipsoid, but a very specific ellipsoid, E23. So this was studied by Dan Cristofaro-Gardiner. His name is really long, so I'm going to write CG. And Aaron Kleinman in 2013. The recursive sequence that shows up in the corners does not have a name, so I'm going to call it Dan and Aaron's staircase. Actually, their result is a little bit stronger than what I'm saying here. What they show, I believe this is true. I believe that it's due to both of them. They show that for all the ellipsoids, there are only a few that have infinite staircases if you put them as the target. And this is one, because the ball is an ellipsoid. The polydisk, you can also write it as an ellipsoid. And in some sense that pertains to this problem in this ellipsoid. So here you have infinite staircases. But in general, if you just look at, you can actually program a pretty good approximation of this function on the computer and then just ask the computer to draw the graph. And in general, there is no infinite staircase. Okay, so what the function looks like is it has a few steps, like maybe 2 or 3, and then it has some mixed behavior, and then it's equal to the volume. But it doesn't have this accumulation of smaller and smaller steps until some point.
General means?
For general x. For x's that we tried. It is very hard to find an x that has an infinite staircase. So
that's just so the Hutchings sequence, that'll always give you the obstructions. They also get constructions.
So you mean
I'm trying to think of, okay, so you always get the obstructions from the ECH capacitors.
Yeah, that's right. Yeah.
But you also need
then you need to show that it actually
exists.
Yeah.
And so here they're using similar when they do these staircases for these other manifolds, they're actually
there are some theorems that help where you don't actually have to construct to have the construction. It just says that I think that one main result that helps is that in order for the symplectic ellipsoid to embed into your manifold, the ball in this case, which is what they proved, you need to think of all the J holomorphic curves of a certain. You certainly need all the J let's see. If you take the ball and you include that in there, you're left with some empty space, possibly. That is has a symplectic form on it, if this embeds symplectically into that. And then you look at all the J holomorphic curves in there, and you have to show that they exist. So it's in this vein. So I don't think that they're actually building they're not giving a formula for what the symplectic embedding is.
But I'm just wondering if they have to reproduce a lot of the arguments like that.
Yes. Yeah, in these other ones. That's right. I think that here, for these two, they get the entire function, and then in this one, they just proved the infinite staircase part. They didn't actually get the mixed behavior and the volume constraint, because they were interested in the infinite staircase part. So one interesting question that we thought was interesting was just, can we find more x's with infinite staircases? So to tell you where we looked, I'll talk a little bit about ECH capacity. So it's a tool for studying symplectic embeddings in dimension 4. A tool, short of there. Okay. ECH capacities. Okay, so given a 4-dimensional symplectic manifold, you can associate to it a sequence of m omega, C1 m omega, C2, a sequence of a non-decreasing sequence, bigger than or equal to 0, a non-decreasing sequence of non-negative numbers, possibly infinite, which are going to be an invariant, and what Hutchins proved was that they obstruct symplectic embeddings. So M1 omega 1 embeds symplectically to M2 omega 2 CK M1 omega 1. Right, so exactly what we had there for the ellipsoids in that direction. Okay, so for all k bigger than or equal to 0. Right. And so very quickly, well, you possibly know better what ECH capacities are than I do, because I'm new to this. I started learning about this stuff when I started working on this. But let's see, if you have a 4-dimensional manifold with a boundary of contact type, let's call the boundary Y, then you can define a chain complex that is generated freely over Z mod 2 by certain sets of Reeb orbits on Y. And then we need a differential. So the differential just thinks of Y cross R, and then you have some finite set of Reeb orbits over here and some down here. And this differential includes, the differential of this guy includes this finite set of Reeb orbits if there's a J homomorphic curve in Y cross R. And then I guess everything, unlike in Joe's world, everything works fine and D squares to 0, and we're okay. Of course, so now you have a chain complex. Now you can, well, now you need some numbers. So let's see. So you take the homology complex associated with it, and then it's if the boundary is like an S3, which for ellipsoids it is, then this ECH is, let's see, I'm trying to remember, because again, I learned this recently. So it's concentrated in even degrees. There's a natural. Just think of how high energy do the Reeb orbits need to be so that you generate up to degree 2k. Okay, and that's the kth thing. Okay, every time that I say this, I'm like learning it better. So, okay, so this is a great result, but an even, and this is due to Hutchins. Then there's a result that is even more convenient for the kind of problem that we're studying, which is this direction for very specific types of M1 and M2. And this is, so maybe in white I'll write Hutchins, and then in purple I'll write Cristofaro-Gardiner. And so this would be if this is a toric convex, concave toric domain, convex toric domain. So I should say what a toric domain is and then what concave and convex are. So a toric domain, if you have, so we have the T2 acts on C2, the usual torus action on C2. We have a moment map. From C2 to R2, and then you can think of some region in R2 and think of its inverse image under the moment map, and that's going to be a toric domain. So toric domain is mu inverse of omega some region in R2. Okay, and then, so for example, this is the ball. this guy like this. This is a polydisk. Ellipsoid. And now I should say what concave and convex are. So I'm not going to write down the definition. This will be a definition by pictures. So a concave toric domain is a domain that is bounded by the x and y axes and the graph of a convex function. And a convex toric domain is bounded by the x and y axes and some convex curve. What I want to say is that ellipsoids are both concave and convex. So those are always on this side. I mean, in my problem, my ellipsoid fits into this type of toric domain. And on the other side, the ball, the polydisk, the other ellipsoid, they always fit on this side. So it makes sense to look for convex toric domains where there's an infinite staircase, because we can use this theorem. And then another thing that is useful to know about convex toric domains is that this example is a little bit abstruse, but you can describe them in the following way. Find the biggest triangle in which the smallest triangle in which it fits. It doesn't have to be the smallest, just a triangle in which it fits. That has a certain size, b. And then find a triangle that you can take out, and then find another triangle that you can take out, and then find another triangle. They have to be right-angle triangles, so it's like blowing up. It's like you have a CP2 and you're blowing up in some sense. Yeah, so you can describe something like this in this way, which is very convenient, because this then also has to do with this is what is left if you have your convex toric domain, then you pack these other balls, then they all fit into this other ball. But it all boils down to ball packings, which is very amenable to being treated with ECH capacities. Okay, so we wanted to find convex toric domains for which there's an infinite staircase for their embedding and capacity function. Okay, so maybe I'll write here the theorem. Theorem. Okay, so Cristofaro-Gardiner, Holm. Again, I'm not writing Cristofaro-Gardiner because it's a huge name. Also, it has an hyphen in the middle, and I have no idea how to deal with that. But so I'm just going to put everyone's initials. It's those people up there. So theorem for these 12 toric domains, there are infinite staircases. Okay, so obviously it's a very stripped down version of what the theorem should say, but you have a lot of context. So I guess I should say what these 12 toric domains are. Also scalings of them and rotations and things like that also. Right, so here they are. So it's these 12, not these 4, these 12. Okay, so you might recognize these guys. They're all reflexive polytopes. So polytopes, lattice polygons with one interior point, one interior lattice point. So that's why I drew these other 4, because this makes the list of all 16. But only these 12 have infinite staircases. These 4 don't. Actually, these even have a bigger problem, which is I'm talking about convex toric domains. These guys aren't even toric domains, but I wanted to draw the entire list. I also put the numbers down here that describe them. So in fact, I could say that it's like these 1, 2, 3, 4, 5, 6. It's like it just boils down to 6 if I'm thinking about the B's and the BI's. But it's nice to have them in this way. Okay.
Could you say that last sentence again?
sort of, in some sense, as far as the way that we in the way that we prove the theorem, we prove these in the same way because they have the same BBI's description. So I could also say for these 6 BBI's, but this is a nicer picture than just writing these 6 lists of numbers.
Did you say there's only one real one that doesn't include?
Yes. Yeah. Also, of course, because I come from more the like toric, symplectic kind of thing, I especially like, let's see, this one, and this one, and this one, and this one, and this one, right? Because they're also toric, symplectic. They're moment maps of toric, symplectic manifolds. But there we go. We also have the other ones.
And so with this lambda x, these guys are your x's?
These guys are my x's.
Are you scaling them like sort of uniformly by lambda? Like, is it just a radial expansion by lambda?
Yeah.
Okay.
Yeah. Okay, so there we go. This is the theorem, and this is very nice. We didn't know it was. We just found some, and then we tried to figure out what the pattern was, and this is what we came up with. So
The dot in the middle is just
the interior lattice point. Yeah, the one interior lattice point. So in the rest of the talk, in the next 20 minutes, I want to do 3 things. One is I want to give you an overview of what the staircases look like for these guys. I want to very briefly outline how the proof goes, because we don't find the graph. We don't actually find this. We think we know what it's going to be, but we don't prove it. What we prove is that there has to be an infinite staircase. So that's quite different from the other approaches. And then I'm going to tell you about a conjecture that we have, which is, well, I can just tell you now that these are the only 12 in some essential way, and why, and that's where the interior lattice point comes in. Okay, so I'm going to need to erase something. Okay, so overview.
Are you guys trying to prove the conjecture before you put the paper out?
Mostly we're trying to write the paper before we put the paper out. It would be nice if we can also prove the conjecture, but I think that we might also, we have a few more things that we want to try. If they work, then maybe we'll include it. If it doesn't work, then we'll just leave it as a conjecture and then work on it for posterity. Okay, so so this overview part also has to, some of the things I'm going to say here is because they're useful for the overview of the proof and for the conjecture part. So the accumulation point is, has some coordinates, which I'll call a0 and square root of a0 over vol, where a0 is the solution of a squared minus ka plus 1 equals 0. Now, of course, maybe I shouldn't write the solution, because there's 2 solutions, but one is smaller than 1, one is bigger than 1. You pick the one that is bigger than 1, because that's what we care about. And I should say what vol is. Vol is basically the volume of this guy. So in the ball, it was 1, so you didn't need this part. Vol is equal to, I need to say what k is. K is vol minus 2. And that's just because vol minus 2 shows up more than just vol. And volume is 2 times area of my omega, my region. Okay, which it's the thing that makes the ball, that makes this ball have volume 1. Okay. So I can tell you about the first sort of mystery, amazing, fun part of this project. We noticed that, so we found some examples, and then we looked up what this number was, and we eventually stumbled on the fact that its negative continued fraction has period 1. which is very tantalizing. It so happens that anything that is a solution to a quadratic equation of this form has this property. So now we've traded this mystery for this mystery. Why is this equation important?
What's at one point that was just like Boston tea stops?
I'll get to that.
Oh, okay.
Philadelphia.
And then this is what you're doing right on top of the fourth.
Yeah, that's like the tau to the fourth. Exactly. Okay, so conjectural exterior corners of staircase. So conjectural because, again, we don't actually prove what the graph is. But we're pretty sure that these are the exterior corners. But we don't need to prove that for our, we don't need that fact for our proof. And here I'm doing exterior instead of interior because that's more useful for the proof. So all that I want to say here is that it's given by some ratios of a recursive sequence. So an equals k, here's that k, minus j plus an minus 2j. There, so a recursive sequence. J equals to 2 or 3. So it's 2 for some of them, and it's 3 for some other ones. So it's 2 for the 3, the 4, 2, 2, the 3, 1, 1, 1, and the 3, 1, 1, 1, 1. And it's 3 for this one and the other one, this one. And one mystery that we have that we don't know what it means is that when j is equal to 2, in the cases where j is equal to 2, so that's like the ball and the polydisk and the ellipsoid, then the interior corners are on the volume constraint. So that's like what I drew. When j is equal to 3, they're off the volume constraint. We don't know what this means. We don't know why this is. Okay. Well, that is, I guess that's a conjecture. That is, we ask the computer to draw the graphs for very good approximations of what the function is. And that's what's happening. I think that it would be easy to prove that these, it's just work, like Cremona transforms and things like that, but it's possible. So this is what Joe was talking about. So the way that we came up with this formula was we would ask the computer to draw the graph with a certain zoom into what we thought was the accumulation point. And then it would give us some points. We would look at the decimal representations and figure out what are the fractions that seem closest to these decimal representations. How can we write them like reduced, not reduced, so that they maybe fit into a recursive sequence, put them into the online database of recursive sequences, and ask the online database of integer sequences and ask what sequences are there that start with this or that include these numbers. And of course, the usual result is you get 5 different things, and then you have to zoom in a little bit more to get a few more and distinguish between the sequences. And every time that you make the computer run, it takes a lunch time or something. There was one time when there was only one sequence. This is like the holy grail of this procedure. And there was only one, so like, all right, we have a sequence. And it was, so 2, 5, 8, 11, 13, 15. It sounds really recursive. It is the numbered stops on the blue line of Philly's SEPTA rapid transit line. So that's like a real-world application of symplectic geometry to mass transit, which I think we could like milk in future grants. Like they can hire us as consultants to see where they should put the next one. No, it's still people still laugh. So whatever. Okay, so these are the two things that I want to tell you because they're going to come up in the next. Okay, so outline of proof, and again, we don't compute the graph explicitly. Okay, so first we have to note a few things about the function C of A, and this was already true for the ball. It's non-decreasing, fine. It is piecewise linear except when equal to the volume constraint. So square root A over vol is the volume constraint. So this is pretty, and this was already true in the McDuff-Schlenk Fibonacci staircase. This is pretty important.
Is that hard? That's the second part.
I think that it was hard to prove when they did it, and now it's an adaptation of their argument. But again, it involves writing C of A not as the, that's just the definition, but an equivalent way is the supremum over some obstructions, supremum of some obstruction functions, and then either no obstruction functions is at play, and then it's equal to the volume constraint, or if it isn't, each of these obstruction functions is linear, so they take turns seeing who's the obstruction in charge. Right. Then 2, for A naught solution of A squared, what was it, minus K A plus 1 equals 0. So at our expected accumulation point, you were actually on the volume. So this one direction is easy, of course. Let's see, this one is easy. That's just volume constraint. The other direction involves something quite interesting, which is these Gerhardt functions for for triangles in this case. So a Gerhardt function, if you have P a polygon, then is equal to the number in a lattice, number of integer lattice points in T times P. Okay, so in a scaling. And if P is an integer lattice polygon, then this guy's a polynomial. If P is a rational lattice polygon, then the Gerhardt function is a quasi-polynomial. So that means that it's like a polynomial, except the coefficients are not constants. They have a period. And in the particular case, when and then when P is not rational, in general, it's just some function, some complicated function without any quasi-polynomial structure. When P is a triangle, the triangle 1 over U, 1 over V, delta UV, of course, the same thing happens. So if U and V are rational, you get a quasi-polynomial. But there are some very specific U's and V's. There's just a few, or they have to satisfy very precise conditions, where they can be irrational, or maybe more pointedly, their ratio is irrational, where you still get a quasi-polynomial. Okay, so if, let's see, is it U plus V equals P over Q, and 1 over U plus 1 over V equals Q times K, where P, Q, and K are natural numbers, then L delta UVT is a quasi-polynomial. Okay, so and that's going to be quite important, because it turns out that you can define So it turns out that for the triangles, if you just think of all the lattice, how many lattice points there are here, that actually has to do with how many integer combinations of certain numbers are smaller than something. So we can show that L delta UVT is equal to the number of k's such that ck of EUV is smaller than or equal to t. So it connects to the ECH capacities. And then we can similarly define for my x omega the number of k's such that how many ECH capacities are below it. And it turns out that showing that this is smaller than that boils down to showing that Lx omega t is bigger than or smaller than or equal to L delta square root vol over a naught square root for all t. Okay, so there's a bit, I'm skipping a bit here, of course, but I just want to say that it ends up being, so this is u and this is v. It ends up being that you're trying to show that this, which is always a quasi-polynomial if omega is an integer lattice polygon or a rational lattice polygon, this is a quasi-polynomial, so you want to find, in those cases, these are also quasi-polynomials, and then you just compare two quasi-polynomials, and that's possible because they're quasi-polynomials, so you just have to check a bunch of cases. Okay, then so that was 1, 2, 3, and I say this because if I get there to the conjecture, then this plays a role. Then the third step is you say, okay, so now I know that there's one point in the graph that I know, that's the accumulation point. Now, immediately to the left of the accumulation point, either my function is equal to the volume constraint, or it's piecewise linear, in which case it either goes in just in a line, or it goes in as an infinite staircase. And then we show that it can't be equal to the volume constraint exactly because we have those conjectural exterior corners of the staircase that are lifting it up from the volume constraint. So it can't be equal to the volume. And then we assume that it's linear, and we use some ECH capacities in some other way to show that it's also not linear. Therefore, it must be an infinite staircase. So
I'm sorry, go ahead.
So the proof is really not very constructive at all. It just says that there must be an infinite staircase. Okay, so.
Did you say you?
Oh. Okay, so very quickly, where the conjecture, I can't prove the conjecture, obviously, because if I could, it wouldn't be a conjecture.
What the exterior corners?
The conjecture that these are the only 12. Which have infinite staircases. Okay, so what we show is that assume that you have an infinite staircase in the embedding capacity function. Then one thing that we can prove is that the accumulation point must be at the A where it accumulates must satisfy, or let's see, infinite staircase must accumulate at a solution of a plus 1 minus square root of a over vol times pair equals 0. So pair just means perimeter of your, of whatever domain you have. Okay, so just count the lattice points around it. Okay, this is very similar to the other equation because we can show that this is equivalent. Being a solution to this is equivalent to being a solution to that, which really looks a lot like that equation, except that here the perimeter and the volume of those guys is always equal. Okay, and then if it has, this we can show, then if it has an infinite staircase, you need to have a really complex behavior. Oh, and we can also show that C of that A is on the volume constraint, I think. Getting a little bit lost here. Okay, so we can show that. Now, if we want there to be a highly complex behavior like an infinite staircase, we think that this can only happen if the corresponding, this guy will be a quasi-polynomial. We think that we can only have this highly complex behavior infinite staircase if this is also a quasi-polynomial. So that means that this has to be true for that A naught and vol. Okay, so now this equation becomes u plus v equals pair 1 over u plus 1 over v equals pair over vol, and this has to be the form p over q, and this has to be the form q times k. Okay, so this omega, whatever it is, its perimeter has to be a fraction, and perimeter over its volume has to be q times k. Now, that's not a very easy thing to deal with, but if you scale this omega that you started with by, here, put an omega here. Scale omega by pair over vol, nu omega prime has perimeter equals to volume. Or, yes, well, volume is 2 times the area. And now we use Pics Theorem, of all things. That's another very pleasant thing, is that you can use Pics Theorem. So Pics Theorem, remember, says that area of a lattice polygon is equal to the number of interior points plus boundary points over 2 minus 1. Okay, well, area, remember, area was 2 times the volume. So this will be vol over 2. Wait, what am I saying? Sorry. Let's see. Yes. Volume. Okay, vol over 2 equals number of interior points. The boundary is just the perimeter, and then minus 1. But I said that the perimeter was equal to the volume. So this cancels. So there's exactly 1 interior lattice point. So that's how we get the 12. So that's it. That's like 2 minutes late. So.
Well, you started late.
Oh, thank you, Joe. Always so positive. Thank you. Okay.